Welcome to Tomorrow Unveiled, the deep dive designed to get you ahead of the curve, translating dense research and technological breakthroughs into high-value insight.
This week, we're looking at a really specific period. The sources compiled by our dedicated research team covered December 20th through the 27th, 2025.
And it was a huge week.
A huge week. What the data shows is that this wasn't just, another week of slow progress. It was a genuine inflection point.
Right.
We're seeing AI robotics move decisively from being this impressive lab demo, something you'd see on YouTube and go, wow, to becoming an undeniable industrial and, well, geopolitical reality.
Absolutely. The convergence our research team documented is it's unprecedented. You have this sophistication in hardware, these incredibly powerful new algorithms, and critical global policy moves all happening at once.
In parallel.
Exactly, in parallel. And that makes the changes so much more than just the sum of their parts.
Yeah, that's the core thesis here, and it's corroborated across all our sources. The machine is truly rising, but, and this is the important part, it's not that single perfect generalist humanoid that, science fiction always predicted.
No.
Instead, what we're seeing is a rapid, distributed industrial transition. The global market is suddenly aligning on what's viable and what can scale.
And as always happens with that kind of rapid deployment, it immediately brings in massive new structural risks.
Huge risks, particularly around cybersecurity and this emerging battle for who controls the global industrial standards.
So our mission today on Tomorrow Unveiled is to really analyze these highly corroborated breakthroughs.
Yeah.
We focused on three major shifts that our research distilled from all this information.
Okay.
First, the new physical capabilities. This is the proof that foundational AI is genuinely working in the physical world.
Then second, the commercial side, the rapid large-scale deployments and the metrics showing who is actually making reliable money right now.
And finally, we have to talk about the emergence of these critical security and standardization debates. They're going to define the entire landscape of this industry in the next year.
And by the time we're finished with Tomorrow Unveiled today, you'll have a really clear understanding of how these foundation models are granting robots something we can only describe as, well, a genuine physical intuition.
We'll also get into why commercial success is now all about reliability and security, not just flashy spectacle.
And crucially, which robot form factors? Is it the general-purpose humanoid, or is it the narrow, specialized machine? Which one is dominating the immediate return on investment? This is a deep dive into the practical, near-term future of embodied AI.
Okay, let's unpack this capability shift. For years, the public idea of a robot was, based on these highly curated, sometimes really awkward lab demos.
Right, always on a flat, clean floor.
Exactly. The sources covering this specific week show that gap between the lab and reality is closing, and it's closing dramatically.
And the most viral, most corroborated demonstration that the research team tracked. It wasn't in some sterile lab.
No, it was on a concert stage with 18,000 screaming fans.
That would be the now famous Unitree G1 humanoid performance at that huge concert in Chengdu, China. I mean, the visibility alone was a massive strategic win for them.
It puts the technology literally under the spotlight, right? It moves it completely beyond that niche tech audience.
And this wasn't just, walking on stage and waving. The research confirmed there were 6 of these G1 humanoids.
6 of them?
Performing synchronized, really complex choreography right alongside the singer Wang Lihong. And then came the moment.
The flip.
The Webster flips. And that got everyone's attention. I mean, our team confirmed high-profile social media posts from major industry leaders, including Elon Musk, who called the move impressive.
So let's analyze the technical side of that, because it's easy to just get lost in the spectacle.
We have to. The technical significance here is that this performance proves an unprecedented level of dynamic balance, high-speed coordination, and real-time motor control, but in an unstructured environment.
A concert stage is about as unstructured as it gets.
It's the antithesis of a lab floor. You have massive sound vibrations, unpredictable lighting changes, the movement of thousands of people nearby.
Just the coordination to maintain balance during those flips, especially all at once and in sync with music, it requires total split-second control over the robot's entire body mass.
Precisely. And the research sources really emphasize that the engineering here was deliberate to make that possible. The Unitree G1 has a height of 1,320 millimeters.
Which is about 4 feet 4 inches.
Right, so it's significantly shorter than some of the, 5-foot-plus humanoids we've seen. And that lower center of mass is absolutely crucial for stability during those high-difficulty dynamic moves like a flip.
And I imagine it also reduces the amount of power, the joint torques you need for rapid motion compared to something taller and heavier.
Exactly. It's a fascinating engineering trade-off. They sacrificed a little bit of that human-like stature for these huge gains in stability and power efficiency.
So it's a deliberate design choice.
A very deliberate one. And the analysis confirmed that this choice, combined with the affordability, it's around $16,000 for the research platform, it marks major progress.
Hmm.
It suggests companies are prioritizing demonstrable, affordable agility over pure, looking exactly like a human in the near term.
It's a display of efficient dynamic control, not just raw strength.
Exactly.
So that covers the dynamic agility piece. But maybe even more foundational for actual industrial use is the move toward absolute precision.
Dexterity. Yeah.
We're moving from running and jumping to being able to manipulate things with almost surgical accuracy. Let's talk about the TARS robotics breakthrough.
This one really caught the attention of manufacturing experts. TARS introduced a dexterity demo that showed a humanoid robot performing two-handed embroidery
Two-handed.
and with confirmed sub-millimeter precision on soft, flexible fabric.
Sub-millimeter precision on fabric. I mean, that sounds less like a robot and more like a master tailor. Why was that task considered for so long an impossible bottleneck for automation?
It's what's called the deformable material problem. Traditional automation needs two things: rigidity and predictability.
Sure, a metal car part is always the same shape.
Right. If a component is metal and you know its exact dimensions, you can program a precise path. Fabric is the complete opposite. It's non-rigid, it's flexible, its geometry changes instantly under stress.
A tiny tug and the whole canvas changes.
The whole thing changes. The robot has to feel and compensate for that at the same time. The research team's analysis shows the success here is attributed to what TARS calls their data AI physics approach, which uses these vision language action, or VLA, models.
So the robot isn't just following a pre-programmed path. It's literally feeling the tension in the thread, seeing the fabric distort, and compensating for all those constantly changing forces in real time.
That's the VLA magic right there. The model is essentially combining high-res visual feedback with tactile and force sensor input. It uses language to understand the high-level goal, embroider this pattern accurately, and then it executes all the tiny micro-adjustments needed for the physical action.
The VLA model is basically a highly adaptive controller.
It is. And this breakthrough is hugely significant. Handling soft, flexible materials with high precision is the absolute key for automating critical manufacturing tasks that still, to this day, rely heavily on human hands.
Is there a specific manufacturing task this unlocks?
Oh, yeah. Think about intricate wire harness assembly in factories. Those harnesses are complex, flexible bundles of wires that have to be routed and connected perfectly.
And it's all done by hand right now.
Mostly. Or, think about textiles and apparel. Historically, these were the last frontiers of factory automation. This level of dexterity, concerned by the sources, it extends the territory that was previously reserved for highly skilled human artisans. It moves us toward the total automation of assembly lines.
So we have Unitree's dynamic agility and the fine motor control from TARS. These show the hardware's really catching up. But what's powering this leap? The research pointed directly to a general algorithmic shift.
Yes, specifically the role of foundation models, granting what the researchers are calling physical intuition.
And that brings us to the findings from this research organization, Physical Intelligence. They basically ran a series of stress tests, right? And Robot Olympics.
They did. The goal was to test these new systems on challenges that were specifically designed to embody more of X paradox.
Remind us what that is.
It's the idea that tasks humans find trivial, like picking up a piece of laundry, are extraordinarily difficult for robots, while things we find hard, like complex math, are easy for them.
So give us an example of a task from these Olympics that embodies that paradox.
Okay, things like navigating a self-closing door. That requires understanding timing and force. Or using a key to unlock a specific padlock, which needs delicate, non-visual haptic feedback.
You have to feel it.
You have to feel it. And then the really messy ones, the deformable manipulation challenges. Successfully using a wet sponge to clean a surface, or handling a greasy frying pan without dropping it. These are all things that demand a generalized knowledge of physics and just common sense.
So what did the results show when you compare the old models to these new foundation model trained systems?
The difference was night and day. On these complex, real-world manipulation tasks, the baseline systems, so standard vision language models, without any robotic foundation model pre-training, they achieved a 0% success rate on tasks like handling that greasy pan.
0%.
0. They just couldn't generalize it all.
Total failure to launch.
Correct. Meanwhile, the systems using these fine-tuned VLA models, the ones pre-trained on diverse robotic data sets, they achieved a 52% success rate on those same difficult tasks.
From 0 to 52%.
The model had learned enough about the physical world to successfully strategize and execute actions in scenarios it had never seen before.
Now, 52% success, up from 0, that's a phenomenal improvement. It's a paradigm shift. But let me push back a little here.
Please.
Is 52% really enough for industrial adoption? I mean, doesn't that still mean we have a long way to go before these models are truly reliable outside of a lab?
That is the essential, critical question. And no, 52% is definitely not ready for the factory floor, where 99% is the minimum standard, as we're about to discuss.
Okay.
But the significance here lies in that generalizing physical intuition it captured. The methodology the researchers use confirms that these large models, trained on all this diverse robotic data, they developed emergent capabilities, the ability to rapidly adapt to new challenges.
They learn a generalizable skill, not just one trick.
Exactly. And the key to that intuition is the efficiency of the transfer learning. The research team noted that this fine-tuning was incredibly fast. It required under 9 hours of fine-tuning data per complex task.
9 hours.
Yeah. If you compare that to the months or even years of dedicated programming that traditional robotics required, it shows that the massive foundation model pre-training has already internalized the basic laws of physics. It makes learning a new skill incredibly rapid.
It's the difference between teaching a child how to tie their shoes versus teaching them the general concept of how to make a knot.
That's a perfect analogy.
Okay, here is where the rubber truly meets the road. We've established the capabilities are there, the agility, the fine motor control, but capabilities are, they're meaningless without commercial viability, without scale, without a clear path to return on investment.
Right.
So let's pivot to where the money is being made and who is scaling fastest right now, according to the cross-corroborated sources.
The biggest, most concrete commercial deployment our research team tracked involves the world's largest battery manufacturer, CATL, over in China. They've deployed their MOZ humanoids in an active battery factory.
And we need to underline that. This is not a press release. It's not a single prototype running around in a corner. This is a real active production line.
That is the single most important metric. The sources confirm this is the world's first large-scale implementation of humanoids on an active production line. And the metrics they achieved, they're crucial. They set the new baseline. The MOZ humanoids got a 99% success rate on plug-in tasks.
99%. I mean, that moves them out of the realm of exciting prototype and squarely into industrial quality control.
It does?
Where did that critical 1% failure happen, and how did they engineer around it to make sure the line didn't just jam up or need a human to constantly babysit it?
That's a great question. The sources indicated that the remaining 1% was usually due to things like thermal drift, so slight variations in factory temperature causing minimal expansion or contraction of components, or maybe a minor wire misalignment.
Things that happen in the real world.
Exactly. But the key engineering insight was the integration of rapid self-correction routines, which were enabled by those VLA systems we talked about.
So it doesn't just stop.
It doesn't stop. When a misalignment was detected, the robot would automatically retry the plug-in task, but with adaptive force and visual feedback. So the successful completion rate on the task itself was near perfect, even if the first attempt failed 1% of the time.
That focus on robustness is absolutely vital. And what about the other big economic metric?
Through continuous 24/7 operation, which no human workforce can sustain,
Yeah.
these robots achieved a documented 3x the daily workload of human workers.
3 times.
This deployment, validated across multiple sources, proves commercial viability in controlled, repetitive manufacturing environments like high-volume battery production. And they're not just plugging things in. They're also tasked with complex quality checks like end-of-line testing, verifying the integrity of sensitive wire harness connections.
So if we look at the cost trade-off, this suggests a massive financial incentive. Even if the initial cost of the MOZ humanoid is substantial, running continuously at triple the speed, the return on investment must be extremely fast in that kind of manufacturing.
Absolutely. When you're looking at continuous operation in a high-cost labor market, that initial robot cost gets amortized very, very quickly. This deployment effectively proves the economic case for humanoids.
Yep.
But in controlled, repeatable environments first.
So the value is in the consistent execution of mundane tasks that are hard to hire for.
That's it.
Okay, that's powerful data showing scale from Chinese companies. But how are the established incumbents, The legacy names like Hyundai and Boston Dynamics, how are they reacting to this rapid deployment?
They're pivoting. They're pivoting decisively toward reliability over spectacle. And they're doing it with a huge engineering overhaul.
Okay.
Our research confirmed this comprehensive AI robotic strategy announced by Hyundai Motor Group, which owns Boston Dynamics. And crucially, they are preparing to debut the new fully electric Atlas robot at CES 2026.
Wait, the older Atlas, the one we've all seen doing the stunning parkour that was notoriously hydraulic, right? Loud, heavy, leaky, power hungry.
Very power hungry.
So what are the engineering implications of moving from hydraulics to a fully electric system?
That shift is huge, and it reveals their entire commercial intent. Hydraulics offer unmatched power density, incredibly fast peak force. That's why the old Atlas could do those spectacular flips.
Right.
But they are inherently loud, messy, inefficient for sustained work, and they require constant intensive maintenance. The move to a new electric Atlas signifies a pivot toward what they're calling the software-defined factory, or SDF.
And electric systems, by contrast, they offer precision and clean operation.
Yes, electric actuation gives you higher precision control, lower latency for fine movements, and critically silent, clean operation. That's suitable for semiconductor fabs, clean rooms, general manufacturing.
So they're repositioning it.
Completely. By moving to electric, Hyundai is repositioning the robot not as a circus performer, but as a reliable coworker. The message is crystal clear. For industrial viability, reliability, safety, and integration are the new capabilities, not flashy high-maintenance stunts.
And speaking of massive commitments, the research team also pulled some critical data on Tesla's ongoing infrastructure build-out for Optimus. The scale of the investment in just the computational training is staggering.
It absolutely is. The sources confirm that Tesla filed permits for a massive 200 milliW Cortex 2.0 data center at their Giga Texas location.
200 megawatts. Can you put that in context for us?
To put 200 milliW in context, that is roughly the equivalent power capacity of a medium-sized city, or enough to run about 162,000 high-end GPUs continuously.
That's not building a model farm. That's building an engine for an entire robot legion.
Precisely. This massive computational investment signals a very serious capital-intensive intent towards starting scaled production by the end of 2026. It backs up their aggressive target of a $20,000 cost of goods sold.
They're building the infrastructure to train a legion, not just a handful of prototypes.
Yes, suggesting they're very serious about their vision of a billion-unit market in the next decade. You need that kind of computational power to really address the sim-to-real gap we'll discuss later.
So we have impressive factory scale with CATL, massive infrastructure commitment from giants like Tesla and Hyundai. But if we drill down to the pure financials, where is the commercial return on investment, the ROI, clearest right now? The data suggests the specialist is winning that immediate financial argument.
Yes, it does. While humanoids generate the headlines and the future potential narrative, it's the specialized robots that are generating clear short-term returns.
Okay.
And the definitive example tracked by the research team is the UPS partnership with Pickle Robot Co.
The dedicated truck unloading robot.
Correct. UPS committed a significant $120 million to deploy about 400 of these specialized robots across 60 U.S. sites. A huge financial commitment dedicated to one extremely narrow, high-volume task.
Which is basically just moving packages.
Just using vacuum grippers and sophisticated vision systems to identify and lift packages onto internal conveyor belts. That's it.
So what was the critical financial finding that validated this specialized approach?
The critical finding was the validated 18-month payback period.
Wow, a year and a half.
That is incredibly fast for capital equipment of this complexity. It completely validates the financial model for these narrow task specialists. If you build a robot that solves one specific, high-labor, repetitive logistics problem perfectly.
And perfectly can even be, what, 80 or 90% success?
Exactly. High 80s, low 90s is perfectly acceptable for logistics. The return on investment is almost immediate, proving the financial model is mature.
That fast ROI directly challenges the whole general-purpose humanoid concept, where the R&D costs are so much higher and the success rate in diverse environments is still much lower, as we saw with that 52% in the Robot Olympics.
Absolutely. The market is rewarding utility. And this is reinforced by other non-humanoid advances, like Deep Robotics. They're a quadruped company focusing on power substation inspection, hazardous environment monitoring.
Right, the dog-like robots.
Exactly. And they initiated their IPO process this week based on doubling their revenue in 2024. They are selling functional tools for specialized, dangerous tasks, where the ROI is calculated on risk of mitigation and reliability, not just labor substitution.
So this all boils down to a very pragmatic answer to that whole ideal form factor debate, wheeled versus legged versus hybrid.
It does. The debate is being answered by the needs of the task. We're even seeing the rise of hybrid designs like the Deep Robotics LYNX M20. It's a wheeled-legged hybrid.
It can switch.
It can switch dynamically. It
Yeah.
uses wheels for high speed and efficiency on flat ground, but it deploys legs to go upstairs or over rough terrain. It's a pragmatic rejection of, ideological constraints. It's just about getting the job done efficiently.
The specialist wins the immediate financial game, even as the humanoid dominates the long-term potential story.
That's the state of play.
It really seems the industrial space is signaling loud and clear that reliability and a rapid ROI roadmap are the absolute price of entry. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
And if you're listening to Tomorrow Unveiled on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review. It truly helps us reach new listeners.
We'll be right back with the security reckoning. Why your future robot coworker might already be wormable, and why the battle for global standards is far more dangerous than it sounds.
Welcome back to Tomorrow Unveiled. In the first half, we covered the technical leaps, agility, and precision, and the commercial breakthroughs, showing that robots are moving to scale. Now let's transition to the structural challenges that always emerge from rapid scale.
Right.
And we have to start with the geopolitical maneuvering our research team detected. This is a foundational battle to define the rules of the road globally.
This is what we're calling the war for standardization, and it's happening right now, spearheaded from Beijing. Our dedicated research team tracked the formation of a National Technical Committee for Humanoid Robots by China's Ministry of Industry and Information Technology, or MIIT. Now, when most people hear technical committee, their eyes glaze over, they think of boring bureaucracy. Why is the formation of this body a critical geopolitical maneuver?
It's anything but boring. It is a strategic attempt to define the global industrial norms, what we can accurately describe as the TCP/IP of embodied intelligence.
The fundamental protocol.
The fundamental protocol. And they're trying to define it before Western nations can coalesce around a unified, competing framework. This committee is deeply aligned with national goals. The sources confirmed it's populated by national champions: Huawei, ZTE, Unitree, who we just discussed, and Xiaomi.
So it aligns the entire vertical stack from the lowest level hardware components right up to the network and the AI models?
That's the goal. So if they successfully set the operating standards first, then everyone else, from Munich to Seattle, has to follow that standard or risk being shut out of the massive Chinese market and facing compatibility issues everywhere.
What's the strategic objective there?
They're aiming to standardize two crucial areas. First, embodied data formats. Right now, every robot company collects data differently: video feeds, sensor readings, force feedback. If the MIIT standardizes exactly how this training data is formatted and labeled,
It can pool it.
they can pool that vast data into a unified massive training set, an ImageNet for robotics, and that would dramatically accelerate their VLA model training through network effects.
That creates a flywheel effect. More data leads to better models, which leads to better robots, which gather more standardized data.
Exactly. And the second area is component interconnectivity. By defining the electrical and logical interfaces between the robot brains, the AI models, and the bodies, the actuators and sensors, they effectively commoditize the hardware chassis. The robot body becomes a generic container.
And if the robot body becomes a commodity, the value capture shifts entirely to the software and the network controlling it.
Precisely. That's why having Huawei and ZTE on this committee is so telling. It suggests creating a crucial dependency on their 5G and 6G network infrastructure to manage these vast standardized robot fleets.
So if you don't use their standards and their network, your robots might not be interoperable.
Or scalable within that ecosystem. This is a long-term strategic play for global tech dominance, shifting the competitive ground from who builds the best hardware to who controls the platform.
That is a stunning insight into the shifting value chain. But there's a terrifying counterpoint to this rapid deployment and strategic maneuvering. The the systemic security vulnerabilities that our research also uncovered. This seems to be the industry's single biggest blind spot right now.
Is the catastrophic security reckoning. The sources have clearly signaled this. The Dark Navy Research Group detailed wormable security flaws in commercial robots, specifically affecting the Unitree platforms.
Firmable.
This revelation is widely being called the Stuxnet moment for robotics because it moves the threat vector from just data theft to immediate physical, kinetic danger.
Stuxnet caused physical destruction in industrial machinery. Wormable, applied to a physical machine that can walk and throw things, it's genuinely chilling. So how did the exploit chain work, according to the research? We need to understand where this systemic failure came from.
The research team outlined a distinct and, frankly, a depressingly simple kill chain. It started with initial access via unsecure Bluetooth Low Energy, or BLE, services.
Which are used during setup.
Right, during the provisioning process. It's often an unencrypted channel. An attacker within physical range could inject command arguments. Once inside, the researchers found a shocking lack of basic security hygiene. The firmware relied on a single hard-coded AES key shared across literally every single G1 unit.
Wait, a universal hard-coded master key for the entire fleet just baked into the firmware of every single robot sold. That's not an oversight. That sounds like catastrophic systemic negligence.
It is the definition of systemic negligence, what many security experts are now calling significant security debt. Possessing that universal key allowed the researchers to immediately escalate their privileges to root access, granting them total, low-level control over the robot's actuators and operating system.
But the truly terrifying part was the lateral movement, the wormable capability.
Correct. The researchers demonstrated that once a robot was compromised, it could use its local wireless interfaces, Wi-Fi, Bluetooth, to scan for and infect other nearby robots using the same flaw.
So one compromised unit could turn an entire warehouse or factory fleet into a rogue swarm.
Exactly. Even if those robots were theoretically air-gapped from the wider corporate internet.
And what was the end point? What was the physical danger they demonstrated?
The final step in the Dark Navy research was issuing a malicious command that overrode the robot's physical safety stops. This allowed the robot to execute a full-force physical assault on a mannequin, demonstrating the capacity for intentional, unmitigated harm.
So this moves the threat from a digital inconvenience, like a system crashing, to an immediate physical danger to human safety.
And property. The implication is profound, especially when you think about that CKL scale deployment we just discussed. If hundreds of humanoids are operating 247 and they all share a single hard-coded key, the systemic risk is astronomical.
Security has lagged years behind mechanical capability.
It has. And this systemic negligence, it's driven by the pressure to achieve rapid scale, but it will inevitably force a regulatory crackdown. The sources strongly suggest that agencies in the US and EU are already preparing to draft mandatory cyber-physical security standards in 2026.
So this will force companies to adopt measures like hardware-based security, unique keys for every device, rigorous testing.
Before they can even get market certification. The Wild West era of robotics, where speedy deployment was prioritized over safety, is rapidly coming to an end. It has to, because the consequences are now kinetic, not just digital.
Let's shift our focus now from the body and the structural crisis to the brain. All these physical feats, the agility, the factory precision, they're meaningless if the robot's AI can't reason fast enough to keep up.
It falls over.
It falls over, or it drops that expensive component. So how are researchers overcoming the fundamental data and processing bottlenecks that dictate speed and intelligence?
The first major breakthrough here really addresses latency, which is the nemesis of speed. Our research team highlighted the launch of Gemini 3 Flash from Google DeepMind. This model is critical because it solves the historic latency-intelligence trade-off.
Can you define that trade-off for us?
Sure. Historically, there was an inverse relationship. The smarter or more comprehensive a model was, the slower it ran. The latency of a massive language model is just too high. That slow, turn-taking pace you see in chatbots is totally incompatible with robotic control loops, where decisions have to be made in milliseconds to maintain balance.
Right.
Gemini 3 Flash breaks this curve. It offers frontier-level reasoning, so high sophistication, but at speeds compatible with those millisecond robotic control loops. It allows for ultra-low latency reasoning.
So the robot can be super smart and super fast at the same time. It avoids that moment of processing hesitation that leads to failure.
Exactly.
And how does the architecture allow for that? It can't just be one single large brain.
No, it's much more sophisticated. DeepMind demonstrated a multi-agent architecture in their famous function-calling kitchen demo. Instead of relying on one slow, monolithic AI to do everything, they decouple the critical tasks.
Okay.
You have a high-level planner, which might be a slower, more creative agent determining the goal, make me coffee and toast.
Hmm.
But critically, they introduce specialized, ultra-fast safety agents, verification agents, that check the feasibility and safety of the proposed action before it's executed.
That's brilliant. It's like having a dedicated lightning-fast safety officer sitting right next to the creative director.
That's exactly it. And this is the blueprint for future autonomous systems, decoupling creativity and long-term planning from instantaneous safety and control. It allows for dedicated fast control loops for balance while still enabling complex, high-level planning.
Now, even with fast reasoning, robots still need training data. And collecting real-world data is staggeringly expensive, especially for complex manipulation tasks. Our research pointed to a significant data efficiency revolution that's addressing this cost bottleneck.
That's right. The field is rapidly moving away from that massive, expensive dataset required mentality. Two critical research developments highlighted by our research team really illustrate this shift: multitask trajectory transfer, or MT3, and unitack hand.
Okay, let's start with MT3. How does that accelerate learning from one demonstration to 1,000 tasks?
MT3, which was developed by researchers at Imperial College London, is a specialized framework designed to get the most out of every single demonstration. It allowed a Sawyer robotic arm to learn an astonishing 1,000 distinct manipulation tasks in a single day, using only one demonstration per task.
One demonstration per task. That sounds like the robotic equivalent of few-shot learning, but for physical motion.
It is few-shot learning for robotics. It works by decomposing the human demonstration into two generic phases: alignment, which is positioning the end effector relative to the object, and interaction, the specific motion needed to manipulate it.
So it separates getting there from doing the thing.
Precisely. By leveraging geometric priors, the robot doesn't have to relearn the positioning every time. It only learns the core motion.
Hmm.
This drastically reduces the need for massive data centers. It's a breakthrough that directly challenges the idea that computational scale is the only path to complex robot learning.
Smart data utilization trumps sheer volume.
That's the idea.
And the second key development, unitack hand, that tackles a different kind of data bottleneck: the sense of touch. As you mentioned earlier, a lot of industrial robots are effectively numb, which stops them from doing highly dexterous tasks.
And unitack hand solves that tactile data problem.
Mm-hmm.
For years, robotics lacked a standardized data format for touch, an equivalent of ImageNet for haptic feedback. So tasks requiring high dexterity, like buttoning a shirt or tying a complex knot, are impossible without that sophisticated sense of touch.
So what do?
Unitack AM created a unified representation system. It projects tactile data from various sensor sources, including human haptic gloves, onto a canonical 2D map based on the Menno hand model.
So it translates the feeling of a human hand, the pressure, the texture, the movement, into a standardized language a robot hand can understand, no matter what specific sensors it's using.
Precisely. And this enables something transformative called zero-shot transfer. A human can perform a complex task wearing a haptic glove, generating a standardized tactile data file. The robot, which has never seen the task and has totally different sensors, can then download this tactile experience and immediately execute the dexterous manipulation.
It's transformative for solving the dexterity bottleneck. It allows robots to learn from massive, aggregated human experience, rather than just expensive machine training.
That's a huge shortcut.
Finally, let's look at the sim-to-real problem. Training a robot in a simulation is useless if the results don't transfer reliably to the physical world, where physics always introduces chaos the simulator missed.
Right, the real world is messy.
What techniques are closing this fidelity gap and making that synthetic training data truly reliable?
The research team confirmed major advances in two areas, targeting both evaluation and generation speed. First, on the evaluation side, we have a system called Polaris. This system uses neural reconstruction from video to create high-fidelity, photorealistic digital twins of real environments.
So you can test the simulated training against a perfect digital copy of the real world.
Exactly. It means researchers can evaluate how well a policy trained in simulation will perform in reality in a highly scalable and accurate way. It drastically cuts down on expensive real-world testing time.
Okay, that's evaluation. What about generation?
To make the synthetic training data faster to generate, we have frameworks like Scenaris. This system provides a fast procedural 3D scene generation framework. Instead of a designer painstakingly creating every simulated environment, it procedurally generates diverse, collision-free training scenarios.
And the speed up.
It achieves a massive 234-fold speedup in synthetic data creation.
234 times faster? That's an exponential reduction in the computational cost and time bottleneck of generating that data.
It is. Together, these systems, Polaris for realistic evaluation and Cineris for rapid generation, are making synthetic data creation faster and more accurate. This directly translates into improved safety and reliability when you transfer those skills from the virtual world to the real world, which is crucial for hitting that 99% industrial success rate we discussed earlier.
This has been an incredibly detailed and fast-moving deep dive into the cross-corroborated breakthroughs of the final week of 2025. Let's quickly summarize the 3 key insights that should stick with you.
First, physical capabilities have crossed critical thresholds, and that's fundamentally validating these foundational AI architectures. We saw breakthroughs in dynamic agility with the Unitree G1 executing flips in public.
And that unprecedented precision with TARS Robotics achieving sub-millimeter embroidery on deformable materials, largely powered by VLA models that are granting genuine physical intuition.
Second, commercial deployment is rapidly scaling, but in highly controlled industrial environments. CATL's MAWS humanoids are achieving 99% success rates and 3x human throughput.
However, the data confirms that the clearest, fastest ROI is currently found in narrow task specialists. That's evidenced by UPS's $120 million commitment to Pickle Robot Company with that validated 18-month payback period. Utility is winning the immediate financial race.
And finally, the structural challenges have well and truly arrived. The geopolitical war for standardization is underway, with China's MIIT attempting to define the operating system, the TCP/IP for embodied AI.
At the same time, catastrophic security vulnerabilities like the Dark Navy exploit, revealing hard-coded keys and workable physical threats, now pose major structural challenges, demanding urgent regulatory action on cyber-physical security.
So given all this astounding progress, what persistent challenges still remain, according to the sources? It's clearly not a seamless victory yet.
No, far from it. The research team noted several persistent challenges that really temper the overall optimism. The first is what they call persistent autonomy ambiguity.
What do they mean by that?
Public demonstrations, like the one with Tesla's Optimus serving popcorn in Berlin, they often remain deliberately ambiguous about the extent of remote control versus true, unsupervised autonomy.
So we don't know if someone is driving it off screen.
Exactly. And that lack of transparency undermines public and investor confidence. It's a critical challenge that needs to be resolved through clear standards.
And what about reliability in messy, unstructured environments?
The brittleness of early robots is still a hurdle, despite those lab breakthroughs. The sources confirmed several documented failures, like the Beijing Half Marathon, where only 6 out of 21 humanoid robots actually finished the race.
What happened to the others?
Many experienced overheating, battery depletion, or just balance collapses. It shows that prolonged, real-world robustness in dynamic public environments is still significantly below human capability.
And of course, battery limitations.
Always battery limitations. Legged humanoids still generally measure operational time in hours, not full shifts or days, which heavily constrains their use compared to stationary or wheeled robots.
Okay, that brings us to our final provocative thought for you to consider as you step away from this deep dive on Tomorrow Unveiled. We've talked about the impressive physical capabilities of specific robots, but we've also seen the rise of standardization and the use of foundation models.
The rise of the machines is not about a single generalist robot winning. It's about who controls the underlying infrastructure.
Right. If the robot body becomes a commodity through standardization, which the MIT initiative and the unit TAC hand research both strongly suggest is the inevitable path, then the future of value capture lies entirely in the software layer, in the AI models and the ecosystem of skills.
Therefore, the ultimate winner in robotics won't be the company that builds the fastest humanoid body, but the company that successfully builds the app store for embodied AI.
Who will allow third-party developers from small startups to major corporations to write specific skills, the apps, they can run reliably on standardized hardware.
That platform king will determine who truly dominates this trillion-dollar industry.
And that is the crucial question that will define 2026 and the decade that follows.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this week's developments in robotics. Do you think the security threat uncovered by Dark Navy will significantly slow down deployment? Or is the industrial scale just too far gone to stop?
We invite you back next time as we continue to explore the future here on Yup.
Tomorrow Unveiled.